It's numerical integration. I think it's very nice introduction to numerical methods. It has quite few nice properties, including graphical nice graphical representation when you can clearly see how it works. You have already done somehow another method with the sorting, but it's very nice. But here we go more truly about introduction to numerical methods. It has quite few nice properties, including graphical. Now it's a little better because I start nice graphical representation. But okay, when you can clearly see how it works. As you can see, you have already done somehow another method with sorting, but it's very nice. But here we go about introduction to numerical methods. I do not plan to cover any nice properties in time of our lecture, so hopefully it will stay that way. But in order, as I start nice graphical representation, so the arrangement will be like that. See how it works. Today we will talk about you have already done somehow another method with sorting. You have very nice. But here we go about introduction to next week. I do not plan my colleague who came here properties and deliver the class that way. And because in order to talk about nice graphical representation, the arrangement will be like that. This is a little longer topic that you have already done somehow. And also to translation is one day. But here we go introduction to next week. I do not plan my colleague who came here properties and so there are also deliver the class that way. And because in order to talk about nice graphical representation, the arrangement will be one change is that this is a little longer topic that I already done somehow. And also to translation here I have one day. So here we go introduction to next week. I do not plan my colleague who came here because so there are also deliver the class and because in order to talk about nice graphical representation, the arrangement will be one change is that this is a little longer topic that I already done somehow. And also to translation here I have one day. So here we go introduction to next week. I do not plan my colleague. I'm also not sure about because of course there are also deliver the classes and because in order to talk about nice graphical representation, the arrangement will be one change is that this is a little longer topic that I already done somehow. And also to translation here I have one day. So here we go introduction and then I will next week. I don't know myself. I'm also not sure about because of course there are also deliver the classes and because in order to talk about maybe streaming of nice graphical so the arrangement will be one change is that this is a little longer topic that I already done somehow. And also to translation here I have one day. So here we go introduction and then I will next week. I don't know myself. I'm also not sure about because of course there are also deliver the classes and because in order to talk about maybe I can see it. Yeah. I hope that now it's better. Okay, because I suppose that despite I have, so I wonder if now it's better. Okay, perfect. Okay. So because now, well, yeah, it seems that there is a lot of, those small details that you have to master when doing this. Because I don't know why now it's somehow okay. I know how it happened, because I fixed it. So okay, so it should be fine. Yeah. So if you haven't heard, the main message from the slide is that next week someone else will be provided this lecture, and it's hard to tell if it will be streamed or it will be just uploaded afterwards. And that the classes here, the classroom will start at 9 a.m. Sharp. So of course I will try to arrange this stream, but let's see, because it's required some proficiency and some preparation. Okay, so let's get to the topic. Yeah. So numerical integration, and you can guess it's about computing integrals. Yeah. So we'll focus mostly on computing 1D integrals. Yeah. So just on the plot. Yeah. We'll have some curve. Yeah, and we'll try to figure out what is this integral. So in practice, this geometrical interpretation tells us that we want to just compute area under a certain curve. Yeah. Because here we'll deal with definite intervals. So we'll start by introducing, this numerical method, tell about how we want to proceed to get the solution, what are numerical methods, what is the difference with respect to those analytical methods. Then we'll introduce two of those methods. Yeah, as you can see here in point 3, it is a so-called composite trapezoidal rule and composite midpoint rule. One topic that we'll deal with a little is about abstraction in programming. This is something that sometimes is troublesome. Yeah, I hope that we'll see why and why it's generally important to use it. And often we use this abstraction because like providers of those packages, like providers of MATLAB, always use this kind of abstraction to deliver for us solutions. Yeah, so it's really, really useful. And depending on how we will exactly end up with time, we'll discuss about testing our software. Okay. So, okay, just about computer integral, just few remarks that what I already said, I think at least twice, that it's really nice interaction. It has very important practical applications because many or just most of the integrals cannot be computed analytically, if you know, yeah, but many of them can be computed numerically. If we can just define this function, we don't even need a function. It's enough that we have just set of points. Yeah, so we can, for example, and this is how like those controllers type PI, yeah, like this integration controller works. It's just integrated using some simple rule, yeah, based on the points. Concept is hopefully well known. Yeah, you have learned about this already a few years ago. Because it's simple, we can discuss about the topics that are a little more important for us, that deals with writing a program, focusing on writing a program in reasonably abstract way, yeah, to abstract some of those details, and to write error-free code, yeah, or at least try to write error-free code. So it also means that, how to deal with testing our written solution. So about integration, once again, I think it should be well-known concept for you. So here we want to calculate integral of some function f of x. Yeah, so we'll deal now mostly with 1D functions. Yeah, on the interval from a to b, and as we know, if we can get antiderivative f of x, yeah, capital F here, then we can compute this integral by just subtracting the value of this antiderivative on both ends. Yeah, it's another thing if we can get it. Yeah, but this is also very useful for us because despite we use this premise that it's often we cannot get exact solution for this interval, so we cannot get exact solution, yeah, analytical solution. We'll use this property for our tests, yeah, because we know on the other hand many integrals analytically, and we'll use it to check if our code works properly, assuming that if it works properly on some those tests that provide exact solution, yeah, that we know, that it will also work for the functions that we do not know analytical solution. Okay, and here's the question about that. Okay, so now we are entering the area of the numerical methods. Yeah, so I hope that after our last classes or from other sources, we are aware that numerical methods are not providing exact solutions in general. Yeah? This type of numerical methods provide just approximate solutions. There are many reasons for it. We'll discuss them, but do you think that should we care about the fact that solution might not be exact?
If I know the error, no. If I know the error of the approximation, I don't care about it. But if I don't know the error, I should care about the approximation.
Yeah. So something on those lines. So in general, it's true that it depends simply. Yeah. So.
But then we cannot find any explicit solution for something.
Yeah, but this is assumption that we in many cases we cannot find. You mean about how to calculate the error?
No, I mean there is no other way around. So I don't think.
Yeah, of course. Yeah. So this is one very good reason. Yeah, but but yeah. So here in general, it's not so important that those solutions are not exact. Yeah, but we should be aware of it. But it really depends. What is the error? Yeah. And we can at least try to assess it. Yeah, for example, by making this the simplest way, because we don't really need to know the error, especially that we don't have, we cannot get absolute error because it's with respect to exact solution, typically not available. But at least like in finite element and many others, there is this concept of convergence. Yeah. That if we calculate it here and we add, for example, calculate it in finer way, a slightly finer way, and we get very similar solutions, so we assume that this is already converged, so those solutions are close enough. Yeah. And so often we don't have choice. It required some awareness. Yeah. But fortunately, in many cases, it doesn't bother us too much, because when we calculate those integrals, usually we don't need it to be precise like today, like 10 digits after the comma. Yeah. Okay. So how to tackle this problem? So if we want to calculate this kind of integral, how to proceed? Yeah. So idea is shown here. It's written here. Yeah. So maybe it will be better to draw it. Yeah. Yeah. So the basic idea, of course, is that in general we have our function. It was function as a function of x. Yeah. So I had this fx, yeah, so we can plot it on the interval from a to b, and it's some kind of function. It's so it looks like that, and we know that if we want to compute integral, of this function on the interval a to b, of course, we have to find a way how to calculate this area, this cross area. So how to proceed? Yeah. So the idea is like, for example, from differentiation. That if we take very small interval, then if we zoom our function, typically this function is have very simple form. Yeah. So here we follow exactly the same area. Yeah. So first step is discretization. Yeah. So this arrow should be longer. So the first step is discretization. Yeah. So I will draw it a little larger. So when you have this interval from a to b, yeah, of our function, whatever it looks like, yeah. So the first step will be to divide this interval into just smaller chunks, yeah. How to divide it? There are many solutions, but if we do not have better guess, we just divide it equally, yeah. So we'll set that a is equal to x0, yeah. Then we'll assume that we'll have n intervals. So b, it will be xn, yeah. And then we'll divide them equally into these equal points. So it will be x1, x2, x3, and so and so, yeah. And here we will have xn minus 1, yeah. And of course we assume, this is required for most of the method, that we know the value of this function at those points. Because if we don't know them, we cannot do a lot about them. Yeah, so it's written here that we consider this kind of integral, yeah, over this interval, and then we will split our interval a to b into smaller ones. And usually points are evenly distributed, and we have done it. Yeah, so here we have also mathematical expressions for this consideration. So if we have n points, then we know that the length of this interval is h. So it's like written here, b minus a divided by n. Here on the right is written xa, yeah, so I think it's pretty simple. So just how to calculate a position of every of those points. And now, knowing the properties of the integrals, yeah, we know that we can divide this integral over AB, yeah, as a sum of all those integrals over those small intervals, yeah. So it means that simply if we calculate somehow the area of that one, of the second area, the third area, yeah, and if we sum up all those areas, we'll get the area of the whole, yeah. So this is the first step, yeah, this kind of discretization. So what to do next? Yeah, because in general, we don't want to, yeah, we will have to evaluate those functions somehow, yeah. So here we at least assume at the moment that this expression of the function f of x is provided for us, yeah, so we can evaluate it. So to solve it somehow, yeah, then over this small interval, we'll assume that our function can be approximated with some function that we know, some simpler function, yeah. And here are some examples. So it can be constant, yeah, very popular approach. It can be linear, another popular approach, yeah. If we zoom it enough, it's very close to being linear. It can be parabola as well, yeah. So there is also a very famous method, Simpson's method, based on parabola. And if we decide that our function is approximated over this interval with one of those functions, it's very easy to calculate this area, yeah? Because, if we have constant, it means that we have just a rectangle, yeah, of the height of f of x at some point, yeah, and another side is h, yeah? If we have linear, it's not much more complicated. Instead of the rectangle, we have trapezoid. Yeah? Is it clear? With parabola, it requires a little more involvement, but still it's doable, and it's not a big problem. And next, like in the last point, is written that we affect the accuracy of those methods, but by varying this interval length. Is it clear why it works? Any doubts? Anything? Okay. So let's say that, yeah, linear functions are not very good because they provide exact solution, yeah, but of course if we have some function like that, yeah, and we want to calculate this integral a to b, and let's say that we'll have very coarse approximation, yeah, just for visualization. So we will use, for example, just two smaller intervals, yeah. So let's say that n will be equal to 2, yeah. So it means that we have x0, x1 here in the middle, because we make this equal split, and b equal to x2 simply, yeah, because n is equal to 2. Then we can find, for example, those 3 points, yeah. The first method that we will introduce will be trapezoidal method. So in trapezoidal method, we'll replace this with simply with the straight lines, yeah. So it means that we'll try to get this area by computing the area of those two trapezoids. And this is the way it works, yeah. Clearly here we can already see the error, yeah, because here we have this small area here, yeah, here and here, those two small areas, yeah, that are our error, because we will assume, because of our approximation, we'll take this into consideration, while of course, you know, our actual function is this integral is smaller. But again, yeah, if we'll increase the number of the intervals, we'll decrease this error, yeah, because like here, if we would to introduce the new point here in the middle, so already, yeah, maybe this drawing is not perfect, but I hope that you can see that, you know, the error will increase quite dramatically, yeah, because if we consider this line and this line, this big chunk, this big triangle of the error will just be thrown away, just by increasing the number of intervals, and instead of using 2, we'll use 4. Okay, so this is how all this works. And here is just on the plot. So we have already seen this, and we have already seen already those errors. So now let's put this into some equations. Yeah, because graphical interpretation is of course nice, yeah, because then it gives us intuition, yeah, but we have to write a code based on this. So to write a code, we need some equations, yeah. This is the preferred way. So the first line here, that line, you have already seen. This is just the split when, and that's why here is just equal sign, because it's not, it's just transformation, yeah. So split from the interval over whole integral into sum of integrals on the smaller intervals, okay. And here approximation happens in this second line, yeah. So here we simply replace our intervals with the area of a trapezoid. Does it require any comment? I think it's pretty easy transformation. Height of the trapezoid is our interval length. Here we have just one side, another side, and just average, yeah. So just standard equation for a trapezoid. And we are writing this area of the trapezoid, of course, for all our intervals, yeah. And then the two next lines, line number 3 and line number 4, are just mathematical transformations, yeah. So we just gather this, yeah, gather all those functions, then we figure out that all values of our functions, values of the functions at all points except of the boundaries are multiplied by 2, because they appear in just two sums, yeah. those two sums. So this middle part can be summed up, yeah, in general way, and we end up with this general solution that is our algorithm that is already fine, prepared to be integrated and implemented, yeah, because here we have just length of our interval, value of the function at start, so at A, value of the function at end, so at B, and here is just sum over all other points. And the reason why we excluded is again because we have different weights here, yeah. So because they have weight 1/2, and they have weight 1, yeah. So there's many ways how we can tackle this, but yeah, this is one way of writing this equation. Any questions? I think it's pretty basic math here, yeah, involved. So what is the next step? Because we already make quite a big, quite a huge work, yeah, because we defined our goal. Our goal was to write a program for numerical integration. We prepare the algorithm, but discretizing our problem, yeah, so a very typical way for solving, for applying numerical methods, yeah. The same goes to finite element methods or this partial differential equations that Alexander will talk with you, yeah. Then we make some simplifying assumptions, so we put a line between the points and then write it in this nice form. So all this work related to preparation of the algorithm, yeah, it's now finalized and it's shown here, yeah. So the next step is
checking the convergence.
No, no. We don't have material to check the convergence. It's a few steps later. Not, yeah. So the next step, okay, so we could make this convergence analysis, yeah, but we'll skip it, yeah. If you mean just from mathematical perspective to make convergence analysis, it would be nice, yeah. But we won't get to this extent. Next step is just to implement it. Yeah. So, yeah. And the following step will be to check it, if program works and if it looks correct, yeah. And the next step, even after checking, should be testing, yeah. Because like for me, I mean by checking that we write something based on this. Fortunately, this is a very simple equation, so also the code is super short, but even in few lines you can make errors, yeah. So the checking, it means that it works, and if you put there some test function like linear, or we'll use one nonlinear test functions just for matter of those tests, then it works on this example. So it means that we finalize our implementation, and this implementation on the first sight looks correct, yeah. Next is testing, yeah, because testing are done, they are considered done when you implement automatic testing. Have you ever heard this term, automatic testing? Okay, so we will get there, yeah, but this is pretty important, yeah. Tests are valid when they are automatic. Maybe you have downloaded, you know, sometimes some software on GitHub, yeah, and sometimes they have this kind of statistics like test coverage, or if it passed last test, and so and so, yeah. So this is connected with this automatic testing. But maybe we shouldn't go too far into the future. We'll cover it, but so the next step will be implementation. Yeah, so now we have this algorithm, we want to implement it. Now, here is discussing two possible solutions and approaches for implementation. So should it be specific or general? In many cases, first implementation is quite often specific. Yeah? It depends, yeah, how complicated it is, or so. But I've seen it many times. Also, our PhD students typically start with specific. If they will go for general, it depends on the task. But this is the way how it goes. Yeah. What does it mean specific? Yeah. Specific, it means that we have this kind of algorithm, and then we can apply it in the way that we will just take some function that we have. We just put this function into this equation, yeah. So let's see, like here we have some function v that is some kind of field or velocity, for example, and we want to get the length, yeah, the displacement, yeah. Then we will replace x by t because we have, so it is because velocity is in time, yeah, and our discretization what is x, which can be displacement or other. From this perspective, is just some abstract value, and then we can replace h by time step, yeah, and just write it. Yeah, that we have function v, we have time step, and then just write the sliced equation by using those values and just code it. Yeah, just write kind of the script. Clear? Yeah. Okay. So then it means that this algorithm with this equation that we derived, this algorithm can just solve our velocity for position, and that's all. And it's written somewhere in our code. Yeah. General solution. It means that we can see that we just derive some kind of algorithm. Yeah. An algorithm is entity by itself. Yeah. So it means that it can be implemented independently of the goal, yeah? Because we can see that we just want to solve some kind of the integral from a to b with n steps for any kind of the function, yeah? And then instead of inputting all those values, we will abstract them out and write a function like here, yeah? So then we can write this function trapezoid because of the method that accepts some function and intervals and this n, and then we can use this general function that is separate entity to solve our problem. Yeah, and then in one line we will write that then we will provide f as our velocity, ab, so from where to where in time, and then n as how fine time grid we are requiring to get, and then solve it. Okay, do you feel the difference between those two methods? Yeah, we'll see this in the code. Yeah, maybe it will be even clearer. Yeah. So as you can see, it's written here in the bold that we should always go for, if we can afford, and we know how to do this, we should always go for the second solution. Yeah, it has quite few advantages, and it follows many of the good programming principles. But let's get into it. Yeah. So now we want to make general implementation. However, I believe that maybe we should start with specific. Maybe I'll change the orders because I think that's because I think the next one is special purpose. Yeah. So I think that we should start with it. I think it makes more sense. Okay, so we'll start with special purpose implementation. Yeah. So it means that here we want to we have some function that describe our velocity. Yeah, it's given like 3t squared et e to t cubed. Yeah. Okay. Someone is deriving with this kind of velocity, and then we want to know what is the path it follows. Yeah, after 1 second. Yeah, so that's why our and the motion starts at time equal to 0. That's why our integral is from 0 to 1. Yeah, and then after putting all those values into our algorithm, we get this just exact expression. Yeah, that here we have this dt. Here we have our function inputted. Yeah, in plain sight. So and that's all. Yeah. By the way, we know the solution. It's nice function, so solution is provided below. And okay, yeah. So once again, now is the question: how do you want to work? Do you want to try to implement it by yourself, or you prefer me on the classes to implement this and discuss, how to implement this? How do you prefer to do this?
I
Okay, so yeah, let's try to implement this maybe. Okay, so maybe I will just unzoom it, yeah, so then we will have it somewhere inside, yeah, and then we have MATLAB, and yeah, like standard, new script. So let's call it trapezoidal special. Let's open our editor, and using this principle, let's start with describing what we have done it, yeah. Okay. So what we should start, yeah. So assuming that we have always, you know, this kind of division on tree, yeah, we have to define some things, yeah. Then we have to execute our algorithm and then, you know, make some kind of this summary. So for example, in our case, it will be presentation of the results and then maybe verification of it, yeah. So we can write firstly that for sure we want to implement our algorithm, yeah. Why it's not working? Okay. Now better. Okay, so here we have our function, yeah, and here we have things to do, yeah. So for sure we want to get v, yeah. So let's start v is equal to 0, for example, yeah. So then we know many things. Let's define n. How many steps do you want to have? It doesn't really matter. 100, for example, yeah. And then we know that our t end is equal to 1, yeah. So our dt will be equal to t end over n, yeah. And now we can just integrate it. Here we know that v, because it will be our solution, is equal to, and just retype it, yeah. T0 is 0, so we can skip it, yeah. So so there's no point. So we can initialize v with this equation to make it even more in line with the code. I name it Tn. So we have T 3 times Tn squared times AXP to Tn cubed okay. And this should account for this last term. Any questions, doubts here? Everything clear? No, asking just in case, it should be. Okay. And now we have to loop, yeah? So for I equal 1 to n minus 1. So exactly as written here, from I to n minus 1. I use I because I is this kind of special variable. It's not super important, but it's just slightly better to do that. And now we can write that v is equal to v plus, because we have to sum all this, yeah, and we already initialize it, so we will just add those values still to v, yeah. That will keep our just solution. So 3 times, here we have ti. So to make life slightly simpler, we can write this ti is equal to ii times dt, yeah. Squared times exp of ti to the power of 3. Okay, and then you can write, or even in a nicer way, print f, yeah. Okay, I forgot about new line character clearly here. Slightly better. So okay. So at least the very first part of the special purpose implementation is done. Yeah. So it means that we just define the basic values, yeah. So what is our solution about? Yeah. So we then we implement our actual algorithm in lines 7 to 12, and then we write something in line 14. Is here anything that make you wonder why this is written the way it's written, or all this is clear? Any questions? Is it the way that you would expect it to be?
The integration point on point 0, is it also considered? Because
No, t0 is 0.
okay, so we haven't considered it in the code if it weren't 0. Yeah, but it's specific implementation.
Yeah. Yeah, exactly. Okay, so we have done the first phase, we have implemented it. Yeah, so, and we can see it works. Now it's time for basic checking, yeah, because we know what is antiderivative, yeah. So our antiderivative is this v exact, it's a function of time, equal to exp to t power 3 minus 1. And now it would be nice to make a basic checking, yeah. So maybe I'll and now I will name as the exact solution that we get from it. So it's just value of this function f at the end at 0, and then we can just type and we hope to see the same number. We didn't, so it means that there is a mistake. Do you know what is the mistake?
The number of integration points.
No. No, or maybe maybe you speak about something different, yeah, because it's related to it, of course, yeah. But there is clearly a mistake, because here it seems that our solution was 171 and actual one is 1, yeah. So, do you know what is the mistake?
We haven't divided it by.
Yeah, exactly. Or multiply it rather by dt, yeah. Because this factor 100 is suspicious, yeah, and of course 100 is here, yeah. So we just calculate the value here into those parentheses or braces, and we simply forgot to multiply it by time step, yeah. So here we have to add that v is equal to v times dt. Now run it once again. And they are quite close, yeah. So it looks reasonable, at least, yeah. So there is of course a question if we make some small mistake, and this difference is because of the small mistake, or this difference is because we simply use too few intervals. How do you think? What is the correct answer? So is it rather the case that we use too few intervals, or just we make some tiny mistake? I don't know, yeah, if you ask me, because I don't have enough information. It requires some more insight, because both options are possible. Yeah. Because in this kind of algorithm, one of the very common errors that are done is something like that you can shift by 1 or just forget. It means that you just are forgetting about some very minor detail. So you are forgetting about one value at the boundary or something like that, yeah. And those errors are not so easy to trace, yeah. That's why we have testing to trace it, yeah, not to bother like here, yeah. So here we will just make a simple checking. We will just add 1 0 here. Computers are now super fast, so we can add million, yeah. Result is correct, but it doesn't prove a point. Because if we have shift by 1, and if you increase the number of those intervals, it means that this error could also be smaller and smaller and smaller, yeah, but still it's there. So that's why this is another reason why we need testing. But okay, let's say that this is a slightly different topic. We'll deal with this in testing. So when we will test, then we will try to also deal with this kind of errors and ensure that this is just, our implementation is just correct from top to bottom, yeah? But it's not the main goal here. Code looks properly. I don't know if anyone here or online can see any errors here. I cannot, yeah. So, but it doesn't mean that they are not here, yeah. Any questions? Okay, so now we'll try to do exactly the same, but by using general implementation. I will just shift the screens because I think it's better for online viewers, yeah. So do you want me also to make this general implementation? And then you will just try to follow it? Okay, so no problem, yeah. So what should I write now? Okay, maybe I will just make my life easier, just slightly easier, yeah, and just make a new function, yeah. new function, and I will why it's not working the way I wanted. It makes life just very slightly easier, because when we just ask for new function, at least we get this very basic template. So part of the solution is here. So we know that here our trapezoid. I will just get rid of it. Just our trapezoid takes f, a, b, n. Do you want me to name those arguments properly? Or you are fine with those short notations? It's not the best one. It's not the best one, but we all understand it, and it will make our life easier, and we can then rename them later, yeah, for later use. So, but we don't know about here. So what should we return from this function? What is the result of this function? Because now we are writing abstract function, and what is the aim, what is the goal of this function? Yeah, exactly. Yeah, so I will call it I. I think it's quite typical in calculus to call it just capital I. It's okay. So of course our trapezoid. So this is function, yeah, to approximate. Okay, so it's used to approximate definite integral using composite trapezoidal method. As you can see, one of the drawbacks of MATLAB is that it doesn't do spell checking, and I don't understand why. Yeah, because I think that it's also worth to spell check the code, comments. Yeah, but it is what it is. So detailed explanation goes here. Yeah, so we can write many things, but it's good to write at least what is the meaning of the inputs and outputs. Yeah, so let's now just write. Yeah, so inputs to the so what is f?
F should be a function itself, or isn't it possible to just give a function to another function?
Yeah, we discussed this. Yeah, yeah, it is.
But for now, it is okay. It's a general one. So.
Yeah. It's function to be integrated. What is a? Yeah. How it's called? Lower interval bound, or? Okay, and the last one is n. So what is n? Yeah, number. Number of how to call it? Okay, number of intervals. So okay, so I just write it in a word that it defines how fine we divide our integration region. Yeah. And finally, we have outputs. and our only output is capital I, and capital I is simply, you know, value of the integral. Yeah. Okay. So we have done most of our work by understanding what we are going to do and what is the meaning of all those elements, and now we just have to implement this function. Yeah. So we can use can we start with h? Yeah, I think that we can start with h. H was defined, maybe you remember, it was defined simply as b minus a over n. Yeah, so this is our interval length, yeah, with division n, because we need h. F is provided, and now we can start already calculating. So we can define a as those elements that are outside of our summation, because of course we will be summing things into our loop. Yeah, so it's 0.5 times f of a plus f of b. Yeah, so this is just initial value. Now what's left into the braces, according to our slides, is just this sum. So again, it's exactly written that we start from 1 and go to n minus 1, and then simply I is equal to I plus f of xi. So we need xi. Xi was simply already defined. I think it was a plus ii times h, if I'm not mistaken. We remember that last time we made this small mistake by forgetting about multiplication by the time step. Yeah. So here we have just interval length, but to avoid it, we have to compute that I is equal I times H. And one fix to comment that I is practically its approximation of the integral, but it's a little minor thing. And that's all, I believe. Any questions? Any thoughts? Okay, so this is, we have implemented it. Now it's time to check it. Yeah, we will check it on the same example. Yeah, because our goal is still that we want to calculate this displacement based on our velocity. Yeah. So we have function here. So to test it, we will just create a script that for checking our trapezoidal. Yeah. So we'll add a new script. I don't know why it works that way, but so now I call it trapezoidal check. I will copy some things from here, or maybe I won't. Yeah, not to get confused. So Okay, so check if trapezoidal function works properly based on GNOME solution. Okay. I will check if I can wrap lines. Okay, I will check it later. I have to, yeah. But okay, code will be visible. So again, we have to define, we have to call our function, yeah. So this is our function header. So we'll calculate v like last time, and we have to provide f, a, b, and n. Yeah. So for our example, f we'll use this nomenclature of anonymous functions. Yeah. Like already I used it once, but I will repeat it here. So 3 times t squared times exponential of t to power 3. Yeah. So this is our function that we want to solve. Let's call it v, because we call it v. Yeah. There is no reason why it should have by any means the same notation as in the function. Yeah. Start of our interval is 0 seconds. Yeah. So rename it to t0. End of our interval is 1 second. So rename it to tn. And n is one setting. Let's use 100. Yeah, similar to the last time. Yeah. And then after this definition, it should just calculate for us the solution already, because we call the function. Function is defined. All the calculations are done inside the function. So now, after this script is done, we should get just proper displacement. Yeah. So I can, in practice, I can copy paste all that remaining part from this script. Yeah. Because here we just write that distance traveled 1 second is v. V is provided from this trapezoid. We get antiderivative the same way because we use the same function. And then we display the exact value. Yeah. So let's calculate it. Okay. So we get exactly the same output, which was which is expected. It's very nice, yeah, to have the same output. It means that we don't have at least syntactic errors in our code, and on the first side it seems to work properly. It gives very similar solution, or even exactly the same. If we increase the number of the steps, again we expect to have better solution. Yeah. I'm even more sure that this code works properly because we just base directly on the algorithm and implement it in abstract way exactly, yeah, like the equations that we have provided. Yeah. However, we still could have, make some small error when deriving the algorithm. So knowing how it should work, yeah, it is in general a good idea to test it still, yeah. But okay. So it's done, it works. Any questions? Okay, so if you maybe recall, yeah, we have done those 2 tests of implementation using this special purpose implementation, like done here. And then there's generic purpose implementation, like done in those 2 files. Yeah. So here is actual implementation of the algorithm, and here is all the rest. Yeah. So in practice, yeah, we replace this line 8 here. Okay, in other way around rather. We replace those line 7 to 13 by this single line 8. And we take extra effort to write a separate function. So I wonder, which approach do you prefer? Okay, you know my preference, yeah. So of course this answer is biased, I suppose, but yeah. Do you can see any reasons to go, in your case, one way or another?
This one works for all the functions, so you could give it anything, but the other one only works for that specific function.
Yeah. Have you found any of them to be easier to implement or harder to implement? Or follow? I think that you have to practice it by yourself to know it, yeah, because really, programming is about a lot of practice, yeah. So here, maybe I will leave it that way. It tries to summarize it. What is the issues with this special purpose implementation with respect to general one? Because in short, we try to make this general implementation to make our life easier in longer term. So it means that we want to use it just to limit the number of the errors that will be introduced in the future. Yeah, and here are written some ways how those errors can be simply introduced by using this special purpose implementation. Yeah, because this is one of our goals. Yeah, the goal of the, okay, so there are different goals of the project. Yeah, if my goal would be to get a solution in 2 hours, yeah, and what was matter is just this single number, yeah, I wouldn't bother with all that, most likely. Yeah, still it's okay, I would, because I can, but in many cases with the new algorithm, it's likely that on this kind of scenario I will just follow special purpose because it's slightly easier, yeah, to follow. Yeah, but if it is even on slightly longer time horizon, it's typically better to go for general solution. Even from this code, yeah, I feel more safe with this general approach because it's easier just to relate this algorithm to this part of the code, yeah, and then verify it for the future. Yeah. So it's a little more hassle because, like, even here we have created two functions, two files, yeah, and it may require some just this kind of abstract thinking. So how it eliminates the errors, yeah? So one thing is exactly like you have said, yeah, that if you have this general, it's much easier to apply to any problem that you have, yeah? Simply, you just change the input, one input, or whatever input you change, yeah, and it works, yeah. For the second one, this function is inserted a few times in the code, at least twice here, yeah. We also have made already some simplifications, yeah, like we skipped the initial point because it was 0, yeah, but it is very easy when you are on the schedule and want to solve something. Very easy to make this kind of omission, yeah, that you don't know the algorithm, yeah, or you forget about it already, yeah, and you forgot that you make this simplification, so you just replace it with another function, and then you have this shift by the initial value. Yeah, it will happen for sure. Yeah, so in just longer term, yeah, it follows that keep it simple and single purpose principle, yeah. So it's from programming perspective, this general purpose is simpler because it's just called here and it works, yeah. And here is a little mess, yeah, like there is some implementation together with this initialization value and some verification, yeah. It's a mess, and if you want to fix something because it's not working, we have multiple places to look for. And if we want, and then we will discover that we need to integrate something else, so we would copy paste this, put it into another part of the program. Yeah, it can quite clearly make a mess. And again, yeah, if you want to calculate this function like here, yeah, now with all this effort, we just have to change few lines here, yeah, this line and those two numbers, and maybe play with this, but we still have to play with this, yeah, and then it works, yeah, without any issues. And here we have to change it in few more places, and still it won't work, because we make this kind of, you know, simplifying assumptions that, okay, well, it was 0, just omit it. Okay. I hope it was good enough example, you know, to present the idea of the abstract way of, or this more general way, because it introduced some abstraction, yeah, because of this function, yeah, and that if we just can, we should follow this this way. That if we have some specific functionality, we should just extract it and put it in separate function. Of course, in practice, it's somewhat harder. So in practice, it's often that you write some longer code, that you check that it works more or less, and then afterwards you start, you know, thinking about, you know, abstracting things out and putting this into the function. But it's pretty normal. But in the end, you end up with the code that has a lot of functions that can be used in many different contexts and are easier to understand. Because also, you know, what is happening here? Something, yeah? Yeah, after, if you take a look at this, after 3 months, yeah, you start to wonder, yeah, what is this function and what is this algorithm is calculating? It's some kind of the sum, yeah? And here we can see, it calls trapezoid function, yeah? And even if you don't remember exactly what is trapezoid, yeah, we can open it and it's written, approximate the definite integral, yeah? And then we can see that, okay, so now it tells us that we calculate integral here, yeah? So we are, so now we know, just after a few seconds, that we are integrating v. Okay, yeah, I have no more comments, but this is the way to go. Anything from your side? Can we go further? Okay, perfect. Yeah. So some kind of the, here we have summary of what I said with some extra stuff, right? You can use it, reuse it. For sure, it's less error prone because of many reasons on longer run. It will save your, it's also save time, yeah? Like the same applies to tests. It takes time to write tests, and at start, it's a burden, but when you write the project, the program that is slightly larger than small one or middle one, yeah, quite soon you will get a lot of benefits by writing tests. Because if you don't write tests, you end up with long debugging sessions. I went this way, and you really can spend some hours debugging your code, because in the 13th function there was, you know, some pivots that it's not working, and yeah, hidden implementation details. It depends on the purpose, yeah. But rather, I would say that, you know, it's also that this is more readable, because it's something here, you know, and from the perspective that, you know, at some point you don't care how it's calculated. You just want to know that it's calculated, what is calculated, and then hopefully that it's calculated properly. Yeah, exactly. The use function should be trustful, yeah? And writing tests and having tests and using it many times, it's the way to make it trustful. Okay, so here we have the next next algorithm, yeah? Composite midpoint method, yeah? So in this method, instead of using trapezoids, we are using rectangles, yeah? And it's called midpoint method because the height of the rectangle is taken from the midpoint, yeah? So if we have this interval from here to here, so to get value of this smaller, okay, it's not the best rectangle. Yeah, this one is larger, so it's nicer of that one. If we have interval from here to here, we will find a midpoint like here, and then get value here. Yeah. And here it is shown how it works more or less, because calculating the area of rectangles it's also super easy. Yeah? So we have just a summation of the length of the interval times evaluation of the function in the middle of the interval, just like written here. Yeah, and it also gives reasonably good results. Okay, just to be sure, any question? Is it clear how it works and why it works? Yeah, and it's written here that it's often more accurate than trapezoid method. Yeah, can you see any drawbacks of this method? There is at least one in comparison with trapezoid method. It's a little nuance, yeah. So the drawback is that it requires extra point in the middle. Yeah. So if we have function, it may be nicer method because of two reasons. Yeah. First of all, it has fewer function evaluations, because in trapezoidal method by one, so it's not a big deal, but still, if the evaluation takes hour, it makes a difference. Yeah. Because for trapezoidal we have to evaluate at all those points. Yeah. And for this midpoint, we just need midpoints. Yeah? So for trapezoid, we have n+1 evaluations, and for this method, we just have n evaluations. So this is advantage. It's slightly more accurate in general in most cases. Another advantage, of course. Disadvantage is that we cannot integrate points. Yeah. So we have a bunch of points, like taking from measurements. Yeah, so like we discussed about this PI, yeah, that for example we want to have this integral element based on our measurements from the actual system. We cannot do this with this method. Yeah, we can only use zero order hold, which is less accurate. Okay, makes sense all this? So now, how the algorithm for this method should look like? Procedure is the same. Yeah, the first line is exactly the same, because the first line tells us just that we will split our integral over full interval into smaller intervals. Yeah, so this is this step. The new part is how we get to the second line, but the difference is that instead of calculating areas of those trapezoids, we have areas of rectangle with the height provided in the midpoint. Yeah, so that's why it looks like that we have HF and just starting point of our small interval, end point of our small interval, sorry, and just middle of it. We sum all this, and again, two next evaluations are just, we just rewrite it, yeah, in order to get summation, like that, yeah. And we can clearly see that we have already fewer points to calculate. But okay, and here is provided the xi for it. So here we have this hands-on, but that one I think that you can make. Yeah, it should be pretty easy. Yeah, because it's very simple to the way it works with trapezoid. Yeah, because the header is very similar, just the function name differs, and the only difference is that algorithm is different. Yeah, but the purpose is the same, so that's why interface is the same, output is the same, and it looks similar, and everything I think that it's needed here is provided on this slide. So how do you feel about implementing this function? Midpoint?
To do it now?
Yeah.
Okay.
Are you okay with this? Okay. So I will take a very short break and stretch my legs. And take a look of what you are doing. And of course, if anybody online has any questions or want to implement it, I will be also glad to help.
Yeah.
Is it clear what you are asking to do? Okay, perfect. You are playing with it? You are gaming with it?
Yes. Yeah, I bought this for baby.
Yeah.
I use it for baby.
Yeah, of course, of course. You know, they are typically good on typing or other things. If they are good for gaming, just Okay, I just put a note to myself not to have this kind of sound issues next time. But okay, let's see how you are doing. You're writing test.
Yes. Yeah, I feel a little bit
No,
anxious.
don't worry. You know, it works for me because I work in MATLAB. Okay, recently I switched to something else, but I was working in MATLAB like 15 years. And so for sure it's easier for me to write the code and to not produce too many errors, at least at the start. And when you have, and you know how they say, who doesn't make errors? Only the one that doesn't try.
Yeah, but the click where it shows issues. It shows number 7. Yeah. No, not that one. Here. It shows you. Yeah. So for sure you have done something strange. Because you get, first of all, you should, really use those commas. Because now it's even hard to tell what's going on. And next you use I.
Ah, yes.
So instead of I, so that's why. Just click where it tells you. No, not that one, other one. Okay, it's 3 times t to 3 plus, why do you have plus by the way?
Yeah, I did.
And why you have t to 3? It's 3t squared.
Why do you make it very here?
I just want to find all the bounds and then put the midpoint in another kind of thing. But
Yeah, it's why,
yeah, it is not much more.
Yeah. And you will solve it down like 1,000 times.
Yeah.
So,
Of course it will, but I cannot see too many advantages. Any questions?
yeah, sure. Okay, so it's fine.
Good. Any issues? Okay, great. Do you have any questions? What?
Yes.
Shift by 100 means that you didn't multiply your solution by h. This h. Well, most likely it looks like no, you multiply h. Divided by 1. Yeah, this understand is what is going on. Okay. So some of you get solutions, some of you get errors, everything is fine. Yeah. So maybe because I have solution prepared here, so I don't think that we have to code it again. Yeah, so I'll just copy paste it here. Yeah. So here's one variant of solution. Yeah, like there are many others, of course. Yeah. Even this variant includes two other variants. Yeah, if you want to get a little more fancy, but not sure if there is a reason for that. But yeah, I think that it follows the same principle. So you have to get age because age is not defined. Then you initialize your results. And as you can see, it's clearly written in different time because it uses slightly different notation. But why not? It gets from here expression to xi. Yeah, slightly better. So it gets here expression for xi, and then just execute this summation. Yeah. So from 0 to n minus 1, it adds value of the function in the midpoint. And because h is constant, it's given here outside. Yeah. And then that's it. Yeah. Now, any questions? I think you are good with this because you either try or get very close to it mostly. Yeah. So if you have some small issues, you can let me know so we can take a look at it. Now it's worth checking. So to check it, I will just take this trapezoidal check, copy paste, change the name to midpoint check. And another nice property is that we can just write here, check if midpoint function works properly based on known solutions. Then we replace trapezoidal but midpoint. And that's all. Yeah. And now we can check if it works. Press F5. No errors. Correct solution. Nice. Will it work for 100? Yeah, so we can see even here that at least for this function it's slightly more accurate because as you may recall for 100 and when we are using trapezoidal method we have this kind of small error like here at the end. Yeah, and here is already gone. Yeah. Okay, nice. Questions so far? Okay, so here's another task, yeah, just to compare those methods. This last point is always, it's always a little annoying because remember about nice formatting, because to really compare it, you have to present it in the way that it allows for this comparison. Yeah. Are you okay that I will just show you how to write it, or do you want to test it on your own? So can we just take a look? I hope that I have it here. Yeah, I should have it somewhere here. I think compare midpoint and trapezoidal method on simple example. Okay, sounds like this is the correct one. So this is also nice to have this kind of comments because then just name looks okay, comment looks okay. So there is likely that also the solution is what you wanted to have. And it looks like it has exactly this function, e to minus y squared, like it's here. Yeah. And it will print results from powers 1 to 20. So n is 2 to this power. Yeah. Then we calculate the solution using one method, calculate the solution using second method, and then we will print number of intervals used, solution given from midpoint, solution given from trapezoidal, and then difference between those solutions. Okay. Again, nice thing of having functions is that writing this code is straightforward, because then we have those functions, so we can use them in different contexts. So once again, abstraction is really powerful concept in programming, and we have all those devices because of it exists. So I suppose that simply name is different. Okay, so I will change name here. Okay. By the way, if you see, there was small delay for those super large numbers, yeah? Okay, so what we can get from it? Does it look the way you would expect it to look?
The two methods are kind of getting closer to each other as we roll the number of integration points.
Yeah, this is one. So here we can see a few things, yeah? So first thing is, once again, what we are doing. So for increasing number of n, yeah, we are calculating midpoint, trapezoidal, and difference, yeah? So first thing to observe is if those methods are stable, yeah? So it means that if by increasing n, we get better and better solution, because in this kind of algorithm, it shouldn't be the way that we increase n and then, for example, accuracy drops. There are cases like that, yeah, but it shouldn't be the case for this kind of simple methods to understand, yeah, because there is no reason why it should drop accuracy, yeah. So first thing is that you can see that here, if you take carefully, yeah, we have this kind of triangle that more and more digits are the same. Like this first two digits are the same in the all, yeah? Then 2 starts to be appearing here, then 0 here, 8 here, 1 here, then 3 here, and so on and so on and so on. In practice, it means that it's converging to some value. Yeah, and it's good, yeah, because we expect it to converge to some value. So, like you were talking about this converge analysis, this is some kind of visualization of it. Yeah, it should get better and better. Yeah, the same applies to trapezoidal. Yeah, in general, we can see that maybe it's slightly less accurate, but it's not so crucial here. Yeah, it's important. It can be crucial for some applications, but it's important. The most important things here that it's also converges, yeah, and it's expressed also here, yeah, that they converges somehow together because the number of those zeros increases, yeah, in the same triangular way, yeah, because as this gets stabilized and converges to proper solution, the same applies to second algorithm. So that's why also the error difference between those two became smaller and smaller. Yeah. It's also another way to get more confident with the method that we are using. Yeah, because we are using two methods and a slightly different principle gives the same solution. It's always nice to have this kind of property, and it cannot be other way around. Okay, is it clear? Okay, so some small remarks about integration just to finalize this topic, yeah? So, first one is there are many numerical integration methods, and some of them are special purpose ones, yeah? So there is this Simpson's rules, for example. It's one of the famous because it has better convergence properties. Yeah, it's based on parabola. If you are interested, you can always you can read about this. there is abundant on information about this topic. Just Google and go to Wikipedia, and you will learn a lot if you want. Another is Gauss, or maybe it should be Gaussian, I have to check it. I think it's Gaussian quadrature. It works on slightly different principle. Yeah, it's very useful. And why it's useful? It's, for example, it's very commonly used in this finite element analysis and many others. Yeah, because this method is known to give exact solution when you integrate polynomials. Yeah, so if you know that your function is polynomial of order 5, then you know that if you will use, for example, 3 Gaussian points, you will get exact solution. Yeah, of course, exact to numerical precision. Yeah. All those methods works on the same principle, yeah. So that they exchange this kind of integral into summation with some weights and x's. Yeah, we can fit here both midpoint, trapezoidal rule, also those two. Yeah, Gaussian quadrature works in that way that. In practice, it requires, I don't know if you can work on data points, maybe, but the issue here is that the Gaussian quadrature optimizes also the placement of the points. Yeah, so it is exact because it put certain weight to certain points. Yeah, and that's why. So it's not the case here that those points are equally distributed like in Simpson rules and our methods that we have developed. But yeah. Like in everything, you know, almost every solution that you want to get in numerical analysis have multiple algorithms, yeah, and you can either use general one or you can but you can also dip a little deeper, get a little deeper into the topic, and choose the correct solution for you, yeah. Another example that maybe you will have here is that if you want to solve the matrix equations or just perform some matrix equations, yeah, the algorithm could look different if our matrix is general and different if our matrix is, for example, symmetric. Yeah, because for symmetric, we can neglect, for example, what is below the diagonal and rely only what is upper, and we can get solutions much faster. But okay. Any questions? So we have learned how to integrate, how to integrals numerically by using two methods. Now you can see that there are also more, and of course everything depends on what is our purpose, yeah, to get this kind of the solution. We talk about abstraction. We have seen, I hope in a reasonably convincing way, that why it's good to aim for abstractions. Then it gives us flexibility, and we can do a lot more with the chunk of code that is abstracted away and provided as single module like a function. And it's mostly everything on our side about integrating 1D functions. So we go to testing. If there is no questions. No questions? Okay. So, like it's written here, we already have done two types of, let's say, tests. It was kind of checking, yeah. But yeah. So we compare it with exact solution, yeah. We have done it for both algorithms, and then we check if this value stabilizes and n grows, yeah. And we have seen that it worked, yeah. So this is really nice. Like written, they are not the strongest tests, yeah. So we could do better. There are some small errors that we can miss. Like, for example, again, in our example, we have the value of the function. Okay, like this is a very simple example. Yeah, we have value of the function that that was 0 at point 0. Yeah, at least one of them. So even if we get exact solution, correct solution, it would also work despite this type of the error that we skip value of the function at the start. Yeah, we could remove it, and both those tests would be would pass. Yeah, at least to some extent. The second one, maybe there could be some issues, but still they would stabilize. To incorrect solution, but still they would. Yeah. So there are better way to do this, and once again, test must be automatic, because if you don't have automatic test, you won't run them more than once. Yeah. So if you would make somewhere some modification to your code, and this is also important to have all the loop running. Okay. So in order to, and also we just see the values on our screen, yeah, and for automatic testing we just have to code it as well. Yeah. So we already discussed this topic, yeah, so now I bring it again, because if you have automatic testing, it means that we will calculate something. For example, we will calculate our approximate solution, we calculate our exact solution, and then we have to compare it. Yeah. Issue is that as we have seen, we cannot compare directly real numbers. Yeah, you have already seen this example. I hope that you remember it. Yeah, that if you have if you define 1 and 2 and you expect to get 3, if you make this kind of comparison test, of course the answer is 1. Those are integers. With integers usually it's not an issue. But if we just make it two real numbers, 0.1, 0.2, and expect to get 0.3, we'll get false. Do you remember this and why it was the case? Okay. So here it just shows if that you can, let's say, test it at home quickly, yeah? Or just let's run it quickly. Yeah? So if we'll just copy this, yeah. So double precision number stores, 16, 17 digits, yeah, and this is because of the finite precision, that we cannot we have limited memory for all those numbers, yeah. And like it's shown here, that why one number is that one, second number is that one, and sum of those numbers is that one. It looks pretty correct, yeah. But the closest number to 0.3 is that one. And there are no numbers. We cannot express any numbers between those two values using double precision for floating numbers of this kind of the computers. Okay? But we have already told it, and the main message is here. Do not compare in your test values like that, except of the integers. Of course, integer is safe. So if you're expected to have one cow, you should have one cow, not 1 point something cows, yeah, or potatoes or whatever, yeah. Like in our case, it's most likely we'll have joints, we'll have bodies, yeah. But those are countable, so we know we should have two bodies, and the system should have 1 degree of freedom. Yeah, it cannot be anything else. But if we compare that the velocity at the end should be 0.1, we cannot make this kind of comparison. We are working with approximate method as well. So what to do instead of this? Instead of this, we know that we have finite precision. We know that this precision gives us around 70 correct digits. Yeah, we know that this precision will drop if we will start. Okay. Oh, sorry. If we will start transforming our number, so if we start computing something, the precision will drop. Yeah. So we compare our solutions with respect to tolerance. Yeah. So for this kind of very simple test that we have two real numbers, yeah, we expect that the actual value that we have computed to the value that we are expecting to get will be very, very close. Yeah. And we express it in the way that we use very low tolerance. Yeah, so we set tolerance to very small number, like here is 10 to the minus 15. It's really small number. And then we expect that absolute difference, or some kind of, we have to somehow calculate this difference, the difference between the solutions that we are expecting to get and we actually computed, is smaller than the tolerance that we are assuming. Does it make sense to you? Or is it requiring any kind of comment? Yeah, okay, great. How to choose our tolerance? Here is one. There was one, indication that I tell that because we know what precision we are expecting to get. So we know that our tolerance can be like 10 to minus 12. 10 to minus 15 is very strict tolerance, but it's okay like in the cases like that. But of course, answer is not so simple. Yeah. The issue is that the computations depend on the magnitude. Yeah, because it's slightly different if we compare the objects that are like stars, so they have like millions of kilometers possibly, so 10 to 12 meters. Yeah, so then 1 meter it might not be a big issue. Yeah, but if we compare the sizes of the cars, then difference of 1 meter is a huge issue. Yeah, so in very short way to tell it, yeah, we are looking at so-called relative tolerance, and here is a very simple test that shows it. Yeah. So let's have this part of the code to MATLAB. Yeah. So K10 is simply the values of 10 to different powers, 10 to 1 to 10 to 10. Yeah. To show that what happens if we change the scale. Yeah, a lot. And then we switch to scientific notation, because then it's just easier to read this. Yeah, because now those are zeros, we don't know what's there. Yeah, so when we have different scales, it's much easier to see those scales when we switch to scientific notation. And here is a very simple test. Yeah. And here is what happens when we subtract the numbers, because this should be give 0, in ideal conditions. Yeah. So it should be a small number, but this is affected by the scale of those numbers. Yeah. So the small number in the range of 1, because first number here is 1, yeah, is something like 10 to the minus 15. Yeah. Next is 0, but this is due to accident. Yeah, because it can just be that way that those bits fits into it. Yeah, but we shouldn't rely too strong on it, because next one is 10 to minus 13. Next one is 10 to minus 12. Again 0, 10 to 10, 9, and 10 to 6. And I hope that now you can observe, yeah, that if we talk about absolute tolerances or absolute differences, like here, they change widely. Yeah. But if we were to talk about relative tolerances, it means that the tolerances, divided by the range of the values that we are operating on, then all those numbers are very similar. Yeah, because if we divide those numbers by those numbers, they are in the same range. Yeah, so this is 10 to minus 13, and this will be also around 10 to minus 15, 16. Yeah. So we can easily express it by modifying this equation. Yeah. So just by dividing this appropriately by K10. Yeah. And now you can see that all those numbers are on the range of something times 10 to minus 16. Yeah. So relative tolerance is a good base for comparison. Exact number can be different, but yeah. Yeah, exactly. So we calculate the C, and we have seen that it gives us value 10 to minus 16, always, difference. Another good way is to use EPS function. Do you know EPS function? Have you heard about this? Okay, so it's very handy for test. It's not accident, of course, that this value is very close to this value. Yeah. Let's say what help EPS tells us. Oh wow, it tells us a lot. Spacing of floating point numbers. Yeah, so we won't read it. You know, I encourage you, of course, to read it if you want. Yeah, but it tells about spacing of floating point numbers. Yeah. So, in general, this value tells us how far are apart two closest numbers in the range of 1, because by default it's called with 1, yeah? So because it's called with 1, so we can see that for the 1 is that value. So if we have number 1, the next number that we can represent using this floating point number is 1 plus this number, EPS. Okay? So that's why if we had this 0.3, yeah, minus 0.1 plus 0.2, we have seen that those numbers are very close but weren't identical. Yeah. So here is the difference between those numbers. Yeah. So if we calculate EPS of 0.3, tada. So that's why this is this exact number. Yeah. So as I have told you, yeah, there is no numbers between 0.3 and 0.1 plus 0.2. Yeah. And this is the reason, because this is the difference, the smallest difference that can be between those numbers, and we can see that it's appearing here. So that's why it tells about how the numbers are spaced. Yeah, and of course this value depends on the range. Yeah, so if we ask about EPS of 10 to 100, it's of course huge number. But you know, it's a matter of perspectives, yeah. Once again, yeah. So 10 to 100 it's a huge number, yeah. So for this number, it doesn't really matter if we, you know, like in the case of the just, you know, billions, the single values or 10 to minus 3, that might not really matter, because or the other case, the scale 10 to 16, it means that if we talk about those, you know, millions of kilometers, we are comparing it with the sizes of the sand or even smaller, yeah, ranges. Okay. Is this all clear and makes sense? Okay. So how EPS can be useful? So it's not. Of course, it's not it's not surprising that if we talk about these numbers and then we check EPS to 10, because the first one was to the numbers around 10, those are very similar, because the same principle applies. Yeah. So we can either use this equation like here, that we will use relative tolerance. So the tolerance will be the numbers divided by just the range of those numbers. Or another way to get a good value of tolerance is to depend it on EPS for our numbers. Yeah, because then if we will get EPS, this function, so spacing for our numbers, we know, you know, what range to expect. Yeah. Of course, this is not something that we can expect, because, but we can, for example, make it like 1,000 times smaller, yeah, or we can square root of it, yeah, and so we have to transform it, because we are not expecting to get exact the accuracy of our algorithm and the level of the spacing, but within this range. Okay. So now how to make it technically, testing, unit testing. Yeah, so we'll try to make unit tests. Have you ever heard about unit tests? Have you ever heard about cursor programming? Okay. Unit testing is extremely popular. It's the most popular way, and I think that almost everybody is using it. Yeah. If they are talking about the test, typically they are using about unit tests. There are different types of tests. Yeah. Unit tests are very popular because then you write something, you test it. Yeah. So it's based on the small units. That's why it's called unit test. Yeah. So you write a function, then you write a test to test this function. You write another function, you can write a test to write this another function. Yeah. If you want to test how the whole your system works, it's slightly different level of the test. Yeah. So unit tests are very popular. So it's right like it's here. Idea is to test small pieces of larger code individually. Yeah. So for example, functions are good units typically. You have to identify a small unit of code and make a separate for this unit. Sounds simple. Unit tests should be standalone. Sometimes it's hard, yeah. So it shouldn't run depending on the outcome of other tests, yeah. So it should. So that's why unit tests are pretty verbose, yeah, because you have to define everything, write test, verify it, and finalize sometimes, yeah. In scientific programming, one algorithm is considered as a unit. Some hint. The challenge is to deal with numerical approximation errors. Yeah, we already discussed about this. Yeah, so we know that the thing that we should do, we should just get some tolerance, and this tolerance can we get from relative tolerance, or we can get it by using the spacing functions. Unit testing as side effect forces programmer to modularize code. Side effect, it's mean here as a side effect of the influence on the programming, and this is very positive side effect. Okay, so I think that, so this is the definition. Let's see maybe how it works in practice, yeah. Writing test functions, yeah. So almost all the languages that I know that are pretty modern has some type of the framework that aids you in writing those tests, because I told you that those tests should be automatic. It means in practice that, for example, you have this kind of the projects, and after 5 years you already have written 100,000 tests, yeah. And of course it's not very feasible to assume that you can, anyone in practice can run those tests one by one or even in batches, yeah. So there is always a framework, so it has typically some convention, and it works the way that you type some comment and it runs all the tests that it can find, yeah? And just in your business is to make that it find all the tests you have written, yeah. And this type of framework is also built into MATLAB, yeah. So I think that if we type here unit testing, we should get here something. Yeah, of course it's too small because of some reasons. No, now it's too large. Testing frameworks. Yeah, so testing frameworks. Script-based unit test. We'll follow the simplest approach because there are some others. Yeah. As you can see, it's bigger topic. Yeah. Of course. It's also important. Here you can see that it's mentioned those unit tests, yeah. And here is the section ways to write unit test, and then you have script, okay. So to make things simple, here are the basic rules for writing this type of script-based unit test, yeah. So the name of the test should start with test. Easy, yeah. So thanks to this, when we run the function run test, I think it's exactly run test in MATLAB, yeah, it will just find out all the scripts that start with test, and he knows that there should be tests there, and we take a look and execute them. Test must be a Boolean expressions B. That's why we need this kind of comparison. So we have a typical way that we have solutions that we're expecting to get, solutions that we have calculated, and comparing them. And then we have Boolean expressions. Is this comparison valid or not? B must be tested with assert function. Yeah. Just like that, yeah. So if we get this Boolean expression that we write assert B, and we write that, some message that will point it out what went wrong if the test is not passed, yeah. Test fails if B is false. It also means that test succeed if B is true. So if you just run test script and all tests pass, it produces no output. So that's why it's also this is by design, so that's why it's also nice to have framework, because framework will show you that it runs 12 tests and all was successful. Yeah? So it has something. For multiple tests, each test must begin with a line starting with those double percentage size. So those are MATLAB sections. You know MATLAB sections? Yeah. So you write tests as MATLAB sections. Yeah. And difference is that that despite your script may work, test can fail. And the reason is that I will tell briefly about this, that those sections, if you run it through test framework, they are treated separately. Okay, so the things that you, for example, declare in previous test are not visible for the next test, while in the standard script they are, yeah. Yeah, and then you can type run tests. So just let's write test function, okay? Okay, so let's close this help. I think that I have it here. There is this is so simple. There is no really point to write it almost. So to show how it works, we use test function that is called add. Yeah, so it's very easy to test it. Yeah. So it's like it's written. The only practical purpose of this is just to present how to write tests. Yeah. So I think no further comment is required for this function. Yeah, it just adds two numbers and returns them. Yeah. So so let's take a look already on the tests. Yeah. So first thing is that so here is the same more or less information that is provided on those slides. Like for example, that the file name of the file should start with test, and it starts test underscore add. Yeah. So it indicates that it will test function add. Each test should be written in separate section. So it's done like here. We have here two tests, and we have two sections. Test checks are done with assert method. Yeah. So everywhere here we have those asserts. If assert condition is true, first argument, then nothing happens. Exactly. And test execution continues. So it means that test is succeed, yeah, so we haven't found any errors and we can continue. If test fails, optional message is displayed, yeah. Note that the single test may have multiple assert statements, like here. After that, you can execute run test command in MATLAB command window. Okay. So first, we take a look on those tests, yeah. So first test, just expect us to get 2, and it's based on the premise that if we compute add function and provide 1, 1, then 1 plus 1 is 2. Yeah. First assert checks if the value is scalar. Yeah, because we can make multiple tests, yeah, and one of the tests is if the something that we get from this function is what we expect. Yeah? If it's scalar, if it's positive, or if it's integer, vector, or some kind of the structure. Yeah, all those are valid tests. Yeah, so. And here is the message that it's shown when the test fails. So it would show that at result must be scalar. Yeah, and we'll point out that error is here. Yeah? The next test simply uses this equal comparison. I put it here because we use integer values. They are represented in double precision numbers, but still they can be represented accurately. And then some extra message, and as you can see, it's with formatting. So it's also possible to put some formatting, and then this computed value will be shown. Yeah. Okay. Second one is the one that we already have done. So we have 0.3 and add two numbers. We already know that we cannot compare them by simple comparison. So I get tolerance here. And the tolerance is 10 times APS of expected value, as we have discussed. It's simple operation, so 10 should be fine. Then we calculate the difference, and for difference we have to use ABS because by accident it can be negative, and then wrong thing happens. So this should also be the test can also have errors. And then the simple answer is that we assume that the difference of our two values is smaller than tolerance, and if not, show this message. Any questions? So we follow those rules that we have a proper file name. We have two tests in sections. We use those assert functions. And now we hope, as I have mentioned, that if we press F5, nothing has happened. Yeah? So I pressed F5 and nothing happens. Is it good? That one?
Oh, no, this one is integer.
Yeah, exactly. Yeah. So if we would put here another test, so just okay. So let's put here another test just to show. Just to show what happens when test fails. Yeah. And so we will put here. And then we can put a message, for example, that expected value is not identical to computed. Yeah, because if it will fail, that it means they are totally identical. So now if we press F5, we get this error. Yeah. So it works somehow. The issue is that it's not really nice, yeah, because then it's the question if it fails or something went wrong and it's not executing, yeah. So it doesn't tell us a lot, especially like here it runs slow. So that's why you can run this command run test, and it's slightly nicer. It takes a while, like everything, but as you can see here. It's written that it found only one test function, so that's why it's right that it's running test add. Here are those two dots, and it shows this progress using those dots, yeah. And those dots means that we have written two tests in our file, so that's why we have two dots here. Okay. We have multiple asserts, that's true, but we have two sections. So it means that we have two tests, yeah? Done, and then we have this summary, yeah? And what is important here that 2 passed, 0 failed, 0 incomplete. So we have 2 tests, all tests has passed, and it takes 0.4 to execute them, yeah? But okay, yeah? And here is in the answer comment we can get some, I suppose, some extra information, just if you really want, yeah. Yeah, so if we want to get some more details, yeah, we can see that in the first test one passed and second not, and in the second one, okay, it's also passed, and yeah, so it seems that it doesn't care too much about how many, it doesn't count how many answers. So okay. No. So if we remove this comment, so we know that now tests should fail at least one, yeah? So now if we just run this run test, it's totally different. So start is the same, yeah, that it's running test add. As you can see, first test went fine, there is one dot, but for the second one, it's written that error occurred. Expected value is not identical to the computed. Here we have our message. Here we have line, so we can directly go to this line, typical for MATLAB. Yeah, it works typically for MATLAB. What else? File summary failed, and here we can see summary. One passed, one failed, one incomplete. So yeah, so typically it's enough to take a look on the summary, and we want to have all tests passed. And if some tests fail, yeah, then we have to start investigating, yeah, and wonder, if you write incorrect test or our function works incorrect, yeah, because there may be many reasons for that. Any questions? Make sense? Yeah. And test works so well because when we work on the project, we modify the project in many different ways, yeah. And sometimes some modifications provided in one element of the code can affect another element of the code, or we try to improve something. For example, we have figured out that we have better algorithm for computing integrals, yeah. But for one specific integral, it gives us worse results, and then, for example, we'll get incorrect some solutions, some matrix computed incorrect by numerical way in other part of the code, yeah. So when you start working with complicated codes, the functionality rely on another functionality. So it's nice to have it tested on all those multiple levels. Or you just have error that you haven't predicted, yeah, for the inputs, and you implement the new thing, thinking that it works one way, but it doesn't. Then you can write a new test to ensure also for the future and some other developments that it will still be covered. Like here with those missing 0.0. Yeah, if we just have this one test, we could still miss 0.0, but then we will soon discover that it won't work. It's not working for another function that have different values at the start or at the end, and so and so. Okay. Questions, suggestions? Does it make sense? Everything? Okay. Let's go a little further. So here is a test procedure that we want to include for our trapezoidal method or midpoint. There are different ways of tests, yeah, but for this kind of the code, it is good to go in the way like that. So one is about having some hand computed results. So it means that you take algorithm, you know how it works, and you just assume that the n is small, yeah, and you just calculate it by hand, and then, for example, use just calculator to add those few numbers, yeah. So here we don't care about the exact solution, because this is another thing. It's more about convergence, yeah, that we get correct convergence. But here is more about that. We know in principle how algorithm should work, because we should divide those integrals into smaller integrals that get all those that then get values of those functions, sum them, yeah. And to be sure that we don't make any kind of this error by neglecting some terms, like the terms at the start or others like that, we wanted to calculate it by hand, because this is another way of solving it, yeah, independently of what we have implemented here. Then we will get this number, and then we can calculate it and compare. And precision for this kind of calculation should be very high. Does it make sense to you? And is it clear why to do this? It's for small n, because other than that we have to rely again on full computer power, yeah, so we have to implement something. So small n is designed here that our problem became very simple in the way that we really can almost write it on the paper and then use calculator or some just very basic MATLAB computations to get solutions that we should obtain. And then we ensure that in all those looping and other stuff, yeah, despite everything, the algorithm takes exactly the same steps. Yeah? Make sense? Or not so much? Do you feel that you understand more or less, why does it make sense to you? Because there are really errors that are very easy to introduce and hard to trace. Another error would be if you would put here n minus 2. Yeah? So now we can clearly see that we have error. Yeah? But when we run this code, okay, this one is big one, yeah. Okay, so that one is big one, yeah. So then it's not so easy to come up with this kind of errors, but they exist, yeah. Like for sure we can remove this part, yeah, here, yeah. At least for this test, yeah, we can remove it, and it will pass. And the issue is that if we have more sophisticated codes, it's really sometimes easy to make this kind of small mistake of one or whatever, and then it still will work pretty fine. Yeah. Here it would be rather less visible because of the function we use. If we put here 2, yeah, then I think that, yeah. Then if we put here 2, you cannot see a difference already. Yeah. Then it's very tiny error. And the issue is that if you calculate it on very small n, and you choose it more or less properly, then all those small issues will be visible. Yeah, because you know that if you use three intervals and nothing cancels, and you have the difference that it's even 10 to minus 12, yeah, then it can indicate the error, because you are expecting to get very good convergence, very good precision. Second one is solving a problem without numerical errors. Yeah. So, for example, we know that it must work with linear function. Yeah. So we can put any linear function, even the one that looks very strange, and still error should be close to 0. Yeah. So this is very handy to calculate. Another one is to demonstrate correct convergence rates. Yeah. We have seen it already that it converged nicely. Yeah. We could make mathematical analysis of this algorithm and get the information that it converges. It has quadratic convergence rate, and we can use this fact to check it if this rate is more or less quadratic. Keeping in mind that typically convergence, as you can see, it's valid for n aiming infinity. So for small n, this might not be valid, But for larger n, it should quite quickly become that the rate is around 2. Okay. I believe that we run out of time. Yeah, I suppose that we should end soon. Yeah, so I will just go through it and leave it for you as home exercises. Okay, you should really practice programming. Yeah, here we are working on very simple examples, very short functions, very simple abstractions. Yeah, so this is the point where you should really take care that you master it. Yeah. So I think that writing tests like that is pretty simple. Yeah. So here we have almost everything. So here we have function, yeah, something like that. Maybe it's not still the best one because he has a 0 here. You can modify it. For small n, it gives you this number, and you should ensure that you get this number with high accuracy. Yeah. So I think like it's, I believe it's very easy to make it running. Yeah. So please do this, yeah, and some of you have written to me when I have some issues with the assignment as well. If you have some issues, just let me know. Yeah, second one is problem without numerical errors. I think that you should also test it. Here you have this kind of function to check, yeah, and yeah, it's easy to integrate as well. Yeah? So it's super easy to get the solution, and the solution should be, once again, with the very, very tight tolerance, you should get it. Yeah, exactly. Oh, especially that antiderivative is provided here, so even simpler. Yeah. Next is about convergence rates. This is a little more challenging. So of course, I'm not discouraging you from checking this. Yeah. I think that after those 2 weeks with PTE, I will just very briefly talk about this to make sure it's covered. Yeah. So I still think that you should be able to solve it. It's slightly more involving because you have to calculate, use this equation. It's even written here, yeah, what you are expecting to get. So if you calculate the errors, if you get the 2 values, because it's not about the errors, because we don't compare it here with errors, but we're expecting these values that are calculated, like E, to follow this rate. Yeah. So simply this value for larger n's, when you compare 2 to each other, should be close to 2, because this is our rate. Okay, so this is aim of this test. More or less clear? If not, you know, I hope it's quite clear. Yeah. So I can try estimating it, and yeah. So it's written again what I have told you in the first sentence, yeah, already many times, that having a suite of automatic tests is just the basic, you know, for it's fundamental for any kind of reliable computing. Yeah, I sometimes, even when I read some forum questions, you know, there are guys that are asking, you know, my company doesn't have tests, should I still work there? And you know, many people gives answer that, you know, you should, if you can, find a better place. Yeah, because you know, it means that it will be some issues. For engineering, sometimes it's not so obvious. Yeah, but if you are in the about computer science, this is for sure true. Have you also ever heard about virtual version control systems? This is another very basic, popular, and very commonly used tool in programming. We'll talk a little about this. Yeah. Okay. Time for assignment. Yeah. So there is this book. I hope that you have already downloaded it. If not, I think it's in the Moodle, yeah. Or I think the link is in the Moodle. You should be able to free, without any issues, download it. So please download it. And task is simple. 3 exercises, yeah, small, simple, slightly more challenging, pretty challenging. Solve them, write a code, write a report, submit report, submit code, and make it look nice. And you have around 2 weeks. Yeah, next assignment I think you will get in 2 weeks from Alexander. But okay, yeah. That's all from my side, yeah. Any questions, suggestions, issues, or anything like that? Yeah, despite that I'm traveling, I will try my best, and I think that I will have time to check your assignments during the next week somehow. Yeah, so let's see. Yeah. If you have any questions, problems, yeah, just write to me. Okay, if there are no any questions or doubts, yeah, so thank you. Yeah, and we will see, it seems that in 3 weeks then. Yeah, okay, so thanks, yeah, see you, bye everyone.